I'm Hyun-Kyu Kim at KIAS, one of the organizers of this conference. I'm very happy to announce that we will begin this conference that has a very exciting list of speakers. I'm looking forward to it, as many of you are too. The first speaker is Professor Stavros Garoufalidis from Southern University of Science and Technology, China, and Max-Planck-Institute for Mathematics, Bonn, Germany. He's going to talk about what are Lie superalgebras good for. Did you turn on the mic?
I did. Oh, you can hear me?
Yes.
Oh. Thank you very much for this wonderful invitation to Korea. I've been in Korea, I think, maybe in '97, my first time, and a few other times in between. It's wonderful. So I want to talk to you about Lie superalgebras, basically. What are they good for? And this is actually what I will talk about is joint work with many people, starting with Rinat Kashaev, Matt Harper, Ben Colley, Manuel Wagner, and if you can spell him, Nicolas Andruszkiewicz. Okay, and just as a general idea, I will talk about Nichols algebras in ranks 1 and 2, and then something called the Links-Gould polynomial of knots, and SL21, and some conjecture about knot polynomial invariants and genus bounds, and then experiments with these polynomials and conspiracy theories. This is probably the thing that you'll remember the most, and something called the Weil groupoid and equivalence of categories. And I'll see if I have more time. There is one more item, if I get to it. Okay. So I came to Lie superalgebras recently through the work with Rinat Kashaev. Recently, maybe 4 years ago. It's not that I didn't know about Lie superalgebras. I did not pay much attention, although we did some work with Sobom Yoon about invariants of, representations of three-manifold groups into OSP21. Okay, so in the work with Rinat, basically what we did was to construct from finite dimensional Nichols algebras with automorphisms. So either finite dimensional or modules that are finite dimensional, we construct with explicitly R matrices which one can then feed into Reshetikhin-Turaev construction to get multivariable polynomials of knots. Okay, so Nichols algebras with automorphisms are, I will not give very formal definitions, but I will give examples that kind of matter. So to begin with, they are Hopf algebras. So multiplication, co-multiplication, and so on, compatibility, but with braiding and with automorphisms. And in fact, we'll maybe look at diagonally braided Nichols algebras. What does diagonally braided mean? It means that you have V, which is a vector space with basis x1 up to xr, and you declare them to be primitive, and you declare the braiding. If you swap an xi past an xj, you get qij xj tensor xi, where q is the diagonal braiding matrix, and with automorphisms, which are the simplest kinds, namely diagonal on the xi's. So there are parameters here, and the parameters are the qij's and the ti's. And if you tune the parameters accordingly, you make something which is finite dimensional, and then you get into the matrices and the multivariable not polynomials. The word multivariable here has to do with these parameters. Okay. So what is the Nichols algebra? It is a quotient of the tensor algebra where you basically kill all primitive elements of degree bigger than 1. That is the definition of the Nichols algebra. And for us, H will denote a diagonally braided Nichols algebra with an automorphism phi. So, given such an object, we can make a definition. In fact, whether it's finite dimensional or not does not matter. We can make a definition, which I'll give it to you in a graphical way. So it's going to go on like this. And like that. Okay, H, 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 H. So what is this? This is an endomorphism of H square, where this is phi and this is antipode. Okay. Just given graphically, and the theorem with Rinat is that if H is finite dimensional, then this R matrix, this left R matrix, there is a corresponding right one, satisfies Young-Baxter. Young-Baxter, which means that R1, 2, 1, 2, 1, 2, where R1 is the matrix tensor identity in H, and 2 is identity H tensor matrix. Yeah, I don't need. That's right. It's for the next one that we need. Okay. Yeah. Thank you. All right. Huh? So, examples of Nichols algebras. First, rank 1. Rank 1 means V is one-dimensional, so V has basis X. The braiding is just a little Q, and the automorphism is T, so parameters are T and Q. And to make finite dimensional quotients in order to get these not polynomials, we can do it in two ways. First, you assume that Q is zeta, this is Greek zeta, which is a primitive nth root of unity, complex nth root of unity, then the dimension is n plus 1. And what we get the ADO polynomials, which are invariants from knots to Laurent polynomials in Z, in zeta. These are the ADO polynomials. Second way to make finite dimensional is when Q is generic, but T is Q to the 1 minus n, when n is greater than or equal to 1 integer, and then we get an invariant which now depends only on one variable, which is the colored Jones polynomial. Okay, colored Jones polynomial. So in this case, x to the n is co-invariant. All right, so already rank 1. So what is the point here? The point is that you don't actually need to know representation theory. This very elementary set of rules defines an R matrix for you, and defines it not just as an endomorphism, but as a matrix, since you have used the basis, and you can compute everything. You don't have to guess the entries. The entries are already given and determined for you. Rank 2. Easier. Okay, rank 2. So V has basis x1, x2. These are primitives as before. How is Qij? And I choose my Qij to be -1. And if I do that, you get finite dimensional quotients or Drinfeld-Getter modules, which I didn't really talk about, in two ways. Either Q is a primitive nth root of unity, in which case H has basis x1, 2, and so on, 2, 1, and so on, of length less than or equal to 2n. So the dimension is 4 times n plus 1. And we conjectured, but later proved with Rinat, that this is the Harper polynomial from knots to zeta here, T1, T2. It's a rank 2 analog of ADO. Second way to get finite dimensional quotients is when T1, T2 times Q to the n is 1, and n is greater than or equal to 1, in which case we can set T1 is T over Q to the n half, and T2 is 1 over T over Q to the n half. Then we get some polynomials, which we call them Vn, whether or not these are Laurent polynomials in T and Q. Okay, and we had conjectured, which we now know, that V1 is the Links-Gould polynomial of nodes. Okay, and this is what brought me, at least, to seriously look at, think about Lie superalgebras. So now I need to tell you just a little bit. Okay, so that was the first part. So LG. Okay, LG means Links-Gould, that's what it means. And it comes from representation theory of SL2-1, which basically means 3 by 3 matrices in blocks like so, where the trace of A minus the trace of D is 0. And that is a super Lie algebra with even part. This an odd part. So you see that, oops, trace of A minus trace of D is 0. So you see this is 4-dimensional because 4 degrees of freedom in A. And this is also 4-dimensional because 2 degrees in B and 2 in C. And the rank of this Lie superalgebra is 2. And it has simple roots, alpha 1 and alpha 2, this being even and this being odd. And Cartan matrix alpha I, alpha j, 2, 0, 0, 2, minus 1, minus 1, 0. It is the presence of this 0 that makes alpha 2 odd. If it was a 2, we'd be talking about SL3. And Dinkin diagram like this. Okay. And SL21, we can break it into the negative parts, the Cartan, and the positive, and this is three-dimensional, 2 and 3. So it has two simple roots, alpha 1 plus alpha 2, but as far as positive roots go, you get alpha 1, alpha 2, but also the sum. And this is even, this is odd, and this is odd. The three-dimensional is because of these three. Okay? And you can even have a basis, if you wish, for H. It is this one, with respect to this decomposition. So everything is explicit. So this simply algebra can be quantized and so on, but even before it gets quantized, the important thing is what are its irreducible representations. And there is a whole theory for irreducible representations of Lie superalgebras determined by Katz. I will just talk to you about finite dimensional irreducible representations of SL21. If you understand this, you can understand the general. This has all the subtleties that the general case has. So they are classified by weight, by highest weight. And highest weight lambda is an integer greater than or equal to 0 and a complex number. And these irreducible representations come in two flavors. They are either typical. Typical means a n plus 1 plus a is not equal to 0, and untypical when it is equal to 0. And the dimension of these representations is 4 times n plus 1. Okay, and now using these representations, one can construct by the ratio taken to right functor polynomials of nodes. Okay, these polynomials depend on the Lie algebra SL21. They depend on the representation of highest weight n minus 1 comma a. Yeah, okay. They are polynomials in T and Q, and n here is greater than or equal to 1 because I shifted down. And LG1 is the original Links-Gould polynomial. So, say it again? Yeah, sorry, I did not say. Thank you. T is Q to the A. Thank you. And the conjecture, I may put it here, with Rinat is simply that LGN is Vn for all n greater than or equal to 1. And we actually computed Vn for, I think at that time, initially with Rinat for about 200 knots. And we saw that this equality somehow held, and based on that, we conjectured it. This SL21. Oh, J. Oh, sorry. For that, I mean the Reshetikid derived functor. I don't know what name to give it. I use J for Jones because that's what it is for SL21. I mean the Reshetikid derived functor. There are also a few things I'm not exactly telling you. Unlike the case of the Color-Jones polynomial, this which can be defined for closed knots. I mean, here we have to break the knot and we have to talk about long knots because the quantum dimension is 0. I'm not telling you about all these things, okay? But there is an equivalence between long knots and knots, as well as zero-framed knots. Okay. Yeah, of course.
So how does this theorem number NA of
This one.
lambda? How does that test?
Oh, here. Yeah. You just. So if you do representation of Lie algebras, I mean, and you put weights on the dual of the Cartan of the Dynkin diagram, and because this is even, the weights are quantized and therefore positive dominant weights in positive integers. But because here it is odd, it is allowed continuous variable. And so what is different in Lie superalgebras as opposed to Lie algebras is exactly this dichotomy, because the quadratic form, I mean the Killing form, is non-degenerate but not positive definite. This is why sometimes the denominator of the Weil dimension formula can vanish, and these are the case of the untypical modules. So this causes major headaches because the tensor product of two typical modules can contain untypical ones. So so tensor products of typical modules are not closed. They involve untypical, and the untypical ones are semi-simple, are not semi-simple, but they have projective covers. So the whole thing becomes a huge mess. If you ever want to do explicit calculations, even understanding these modules, I think understanding the fusion rules for SLMN is not known, only for modules.
Is there any geometrical or physical meaning of those numbers? C, A?
Well, in superconformal field theories, there is a paper of Nam, actually. I want to say yes, there are dimensions of like superconformal blocks. If that's an answer. Okay, so we conjectured it. And later we showed with a subset of these collaborations that the conjecture is true for n equal 1. And the way we showed that is the very hard way, namely, there is Skine theory for LG1 and V1 in terms of relations with 3 terms, 12 terms, and 80 terms, in the braid group with 2 strings, 3 strings, and 4 strings, with unique solution. So already in the braid group with 3 strings, it is not a quadratic Skine relation, it is a cubic Skine relation. Okay, so then we check that the R matrices of both invariants satisfy these relations. The coefficients of these relations are kind of scary. I mean, they are rational functions in 2 variables, but yeah. Okay. So later, we also showed that it is true for n equal 2, and this time it came from a cabling formula for LGN. So let me tell you a little bit about that. Oh. Okay. So what this basically says, so okay, here it is joined with Harper, Kashaev, Coley, and Wagner. It says that if you take the LG1 of an N0 parallel of a node K, then you're going to find out some sum with some coefficients, which I'm not going to write down, of LG of K plus 1 original node T to the N, T to the L, Q. And this comes from, these coefficients are explicit and of course do not depend on the node. This comes from the fact that if you take this 4-dimensional representation and you square it, you get 0 to A and 0 to A plus 1 and 1 to A. But for future delights, I will tell you what happens if you take the 8-dimensional representation and you square it, and you're going to find 0 to A plus 1, 0 to A plus 2, 2. V1 to A plus 1, and 2 to A, and 2 to A plus 1, and 3 to A. So far, these colored Links-Gould polynomials are analogous to the color-Jones polynomial, with the only difference being that the SL2 color-Jones polynomial uses only the usual variable Q, which is present everywhere. However, this one has an extra variable T, which comes from the superstructure. So, another theorem of the same people here, GH-KKW, is that if you now specialize Links-Gould to Q equal 1, usually Q equal 1 kills knot theory completely. That it does for the Collo-Jones. But here it doesn't quite kill it because the square of the Alexander appears. Next theorem of Colli and Tahar is that the degree of Links-Gould on a knot, the degree with respect to T, and by that I mean the maximum degree minus the minimum degree, since it's a Laurent polynomial, is less than or equal to 4 times the genus of the knot K. Genus means the smallest genus of a spanning surface. Of a ciphered surface. Okay? If you put these two together, you get a sandwich corollary, which is that twice times the degree of Alexander is less than or equal to the T degree of LG 1 and less than or equal to 4 times the genus okay. And if you use even more results, namely the Cabling formula, which will only work if the coefficients which do not depend on the knot are aligned in their T degrees correctly, and they are, to tell you that twice times the degree, this is not a typo, is equal to this. For all n greater or equal to 1. Okay? So the bound that we had for 1, now we have it for all. Okay. So the natural question is, what happens to these bounds? I mean, how good can these bounds be? Before we get too excited about this, I give you a little fact. LG1 is mutation invariant. And the reason it is mutation invariant is because, where is it? The tensor product of V0A square is multiplicity free. Multiplicity free implies mutation invariance. V0 is multiplicity free. But LG2 is not mutation invariant, right? Because this is not multiplicity free. I say, wait a moment, okay, it's not multiplicity free, but maybe mutation is always so nice that it works. It doesn't. Okay. Good. So now we have a definition. We say that a knot K is tight if the degree of the Alexander polynomial is genus, twice times the genus. Okay, and otherwise loose if the degree is less. Okay, and there's a little fact. If K is alternating or fibered, then it's tight. So So let's look at the values. How much time do I have? 20 minutes? Okay, very good, very good. So then, oh yeah, that requires what my Aussie friend says, heavy lifting. Okay, so let's look at values of LG1, which is V1, and LG2, which is V2. So for that, for loose and tight knots, but maybe B. Yeah, okay. Well, that means you have to compute V1 and V2. And when I mean compute, you have to really compute, okay? Professionally compute. Computing, I mean, well, for V1, it's defined by a 4-dimensional R matrix, and for V2, for an 8-dimensional. So if you want to do this for all knots with, let's say, 18 crossings, naively, you have to place to every little arc that you see a factor of 8. There are as many arcs as twice times the number of crossings, and if C is 18, this is naively what you're dealing with. Okay? Okay. So, okay, crossings. And let me put here, I have it down. Crossings. Okay, less than or equal to 10, 11, 12, 13, 14, 15, 16, 17, 18. And how many notes? 249, 552, 2176, 9988, 46,972, 253,000, 1.3 million, 8 million, and 48.2 million, and actually 19, which will soon be done. It's only 294 million. 4.8 million. Okay, and out of these notes, how many are loose? Loose. None with 10 crossings or less. 7, 29, 208, 1220, 6319, 48174, 303K, 2 million, and 13 million. Okay, so when does V1 fail to detect genus? What does that mean? It means when is this inequality here not an equality? When does it fail? It doesn't fail here because everybody is tight. Here it fails 7 times. Here it fails 20 out of 29, 173, 974, 5,025, 37,000, 228, K, 1.4 million, and this one we don't know yet, okay? But we will know soon. When does V2 fail? 0. Never fails. Never. For up to 18 crossings. 19, we're doing them. We're down to checking the last 3 million out of the 300 million left. And we will know in a couple of weeks. Okay, this is the zoo of examples. So with 11 crossings, there are 7 of them that are loose. 7 loose with 11 crossings. And 2 of them are the famous pair, Kinoshita-Terasaka, 1, and 34 and 43, with genus 3 and 2, and degree of V1, 6 and 6. You see they are mutants, so they have same degree, and degree with V2, 12 and 8. 3 times 4 and 2 times 4. Okay, these are 2 out of the 7 loose ones. Okay, so now I can, so already this is data, yeah? But now I want to tell you, after we compute it, V1 and V2 for all nodes up to 16 crossings, we can look at V1 equivalence class. Okay, we already saw that V1 is mutation invariant, so mutants have equal V1. But for nodes with less than or equal to 15 crossings, mutants and only mutants. Okay? For all I know, this is the universal mutation invariant. We also have the values for 16, except that there is no table of mutant nodes for 16, so I cannot check that all the V1 equivalence classes, and by the way, this V1 equivalence classes for 16 nodes includes 8 nodes. Yep. Oh, yeah. Absolutely. Thank you, 42. Yes. Now we said V2 is strong. It seems to detect genus. Yeah, so V2 separates nodes with 11 crossings, but not with 12. And with 12 crossings, there are 3 pairs. I'm going to give them to you. 3 pairs with the same V2. So 12 and 364 and 12 and 365 mirror. 12 and 421, 12 and 422 bar, and 12 and 553 and 556 bar. So these have same V2. They are mutant. Hegarth-Floer, so mutant nodes generally have different genus. And Hegarth-Floer typically detects mutation. Yeah, sure. So these are these 2 nodes, which are mutant, okay? These 2 nodes have same, okay, V1, V2, V3, V4, because we compute it. They have same Hegarth-Floer, they have same Khovanov, and they have same odd Hovanov, odd. And they have same, well, of course, Color-Jones because it's mutation invariant, and Homfly. But they are really different. The length spectrum is different. They're hyperbolic knots with different length spectrum. Okay, and we actually believe that these knots have equal Vn for all n. And in fact, we have an idea somehow how to show. Also, we have an idea how to, so with my, I should say, all this is joined with Shanna Lee. The computational part. So this particular tangle here, if you glue it to make knots, we expect that it will have equal Heegard-Floer. That is a little project to do, but we haven't done it. And it'll have equal Hovanov. That's another project to do. Before we actually proved it, before we prove it, we just check it by sticking other tangles here and computing, and we did that up to 24 crossings, because you have 6 here, and you can do, I don't know, whatever, 14? No, 14, 16. 6 and 16 make 24. So if you check it for closures, 24 crossings, probably it's correct, and then you can try to prove it, and we have ideas to prove it. These ideas have to do with combing of chain complexes. I could give a whole talk about 12n 365, just it's easy to remember. 365 days in a year, 12 months. Okay? And it's not alternating because it's not tight. Okay, so more, so V2 fails to separate. The genus should change, but it doesn't. Why? Why does the genus not change? We don't know geometrically why it's the case, but we do know experimentally that it is the case. Here is another thing. What happens when K is alternating? Okay, now we're moving into the conspiracy theory part. I already mentioned you a little bit of conspiracy there. When K is alternating, and you compute the polynomial V1, and you replace t by minus t, and you do the same thing with V2, you replace t by minus t, you get what? Has greater than or equal 0 coefficients for all knots K with 18 crossings. Okay, that's a lot of knots. I mean, there are 4.8 million, there's about 3 million of them alternating. No, 2 million, at least, alternating, okay? Why? Maybe it's an accident. I don't believe so. Maybe it's a conspiracy theory. Actually, now the real question is, what's going on with this t, actually? Is this t secretly a categorification variable? But to answer this question, we need categorification for Links-Gould. And, well, I'm asking the experts. I would really like to know how to categorify Links-Gould, okay? Okay. So then, I have 5 minutes. Very good, because then I can tell you about 2 things, maybe at least one thing. So one thing is that this coincidence. So this conjecture that Vn is LGN for all n greater than or equal to 1, it is conjecture, but there is proof in progress. So I call it conjecture proof in progress joined with Rinat and Nikola Andruszkiewicz. So basically, the point is that Hopf algebras with diagonal type, they have an action of a Weil groupoid. It really is a groupoid. It is a group only in the case of simple algebras. In the super, it is only groupoid. And this action of Weil groupoid induces an equivalence of braided tensor categories. And so this is some general theorem. The action is explicit, as explicit as the Lustig operators. But I want you for a moment to stare the similarity or difference between this Cartan matrix for SL21 and this one, the kind of classical version of the Cartan for the Nichols algebra here. So what is going on? I told you that SL21 has 3 simple roots. These 2 are also a basis of the Cartan. Sure. You can compute the inner product using these 2. If you compute the inner product, you find this. Okay? So SL21, as we know, that leads to LG, has to do with this matrix. Vn has to do with this. So there is an equivalence, and that implies from kind of first principles this conjecture. Okay, beyond SL21, I think I have only 2 minutes. Okay, life does not end in SL21. Yeah, okay. So beyond SL21, well, you have to talk about Lie superalgebras of a specific type. So there is a conjecture, again, with proof in progress. That says the following, that if you take the t degree of any Lie superalgebra of type 1, like SLMN, okay, and you compute the polynomial that has one special variable t here, because there's only one t and there's many n's, and the conjecture is that this degree is less than or equal to 2 times the number of odd positive roots times the genus. Here there were 2, and greater than or equal to this times the t degree of the Alexander. Okay, this is called the MMR conjecture, which is a theorem with Dror, Bar-Natan for simple algebras, and you can extend it to Lie superalgebras. That is actually not very hard. And this one, there is an idea of proof. That's why I say it's proof in progress. But if you put this together, it basically tells you that there is only one kind of magic t, and but in this case it is very hard to compute because if you did SL 3,1, the simplest representation would be 8-dimensional already. You have to write down the R matrix completely and make sure it satisfies Young-Baxter, and then try to compute. But that will probably be mutation invariant, so you have to go to the 16-dimensional one, and then things start getting kind of scary. So yeah, you may like this generalization, but keep in mind that it is not supported by experimental evidence, so it may be incorrect. Or maybe you prove it, but still incorrect. But nobody will be able to find a counterexample because they will not be able to compute. Okay, I stop here.